Welcome to data698 final presentation by Weizo. Today's presentation is going to focusing on a project that I worked over the past several months. The topic is Cyberbank Russian housing market, a Kaggle competitions on predicting real estate price in Russia. So before we dive into the details, I would like to give you a little bit more background about this project. So the Cyberbank is the Russia's largest bank, is trying to help their customers trying to make predictions about real estate market. And so the developers, the renters, the lenders are more confident when they sign a lease or purchase a building. So, enabled to realize this goal, Cyberbank released a very large real estate transaction data set with more than 70,000 rows of transaction data with more than 200 features. Share this data with the Kagglers and helping them they could develop a time series forecasting models using transaction data and macro economy data, uh, and use those data to predict a certain house final closing price. So this is all this project's about, trying to use housing related data, macro economy data to predict housing prices. So now comes to the questions. What is the questions? Research questions about this project. That is using a machine learning based methodologies to predict the real estate price. And now we know the background of this project, the research questions, let's dive into the data. What are the data that are shared by the Cyberbank of Russia? So here are the data. There are mainly two sets. Um, According to the type of data, it can be divided into real estate related data. That is like how many bedrooms house does a house has, how many square feet this house has, and the labor is the total closing price of this listing. And the other type of data sets that the Cyberbank provided are the macroeconomic data, which are the ratio between US dollars and Russian dollars and some other features that are related to the overall macroeconomic environments. And the time frame is mainly from 2011 to 2016, and they're asking us to use this data to first train the model and then use 25% of the data as the testing to see evaluates the model's performance. Now we have a basic idea about what does the data looks like, how we're going to tackle these problems. So this project workflow, also known as the model development phase, can be mainly divided into four stages. First one is data assessment. We need to have a more detailed look, comprehensive image about this data. How does each features are related to each others? We also call this exploratory data analysis, EDA. And after we gain a better understanding about the data, we need to prepare for the model trainings. That includes the data cleaning, the feature selections, and data reengineerings. After we all did this, we need to choose the model that we want to use and use the data that we prepared to train the data. Um, so this is a reiteration process. We understand the data, prepare the data, train the data, and see the performance of the models and see if we can improve of any elements of this model. For example, adding more features, decrease number of features, doing more feature engineering, and redo the model training to see if the model's performance has been improved. So this is a reiteration process that allow us to improve the model time and time again. So now we came to the first part, that is the data assessment, which we also call exploratory data analysis. Let's know more about this data. So first thing first, let's look at the most important data in this data set, which is the price, because this is our research problem. How much should a certain listing house being cost on the market? How much a buyer should pay for certain listings? And we see this pricing in a time series trending, and we can see overall trending from 2011 to 2016. There is an increasing trending of the total price of the overall housing market in Russia. And we can see there is a dramatic increase around the middle of 2012 and goes down at the second part of 2012 and then dramatically goes up and down, and but the overall trending is showing going up to 2016. Um, However, these are based on the overall price, the total price of certain houses. It does not necessarily telling you what is the unit price, how how expensive a house is. It isn't just it could say uh, one 1,000 square feet costs you $1 million, and also there is a house that is 10,000 square feet also cost you $1 million, but you will feel that the 10,000 square feet houses was one uh, that price is much cheaper than the one that has a uh, smaller square footage. So here we need to do some data transformation that I used the price per square foot and then to see the overall trending. Now we can see a much more clear trending about the unit price per square meters over time. There's a price drop in late 2012 and showing an improvement after 2013. And in the later of the model training, we will keep using this average price per square feet as the label. And when we predicting the housing market, we're still using the output will still be the average price per square meters, but we will times the actual square meters of that house and becomes the final total price of certain houses that we predicted. Price by apartment size. So median prices goes up relatively to apartment size, except large apartment price is slightly lower than the median apartment. So this is a box plot, easy to see. Priced by the building size, again, sky building that was higher, median prices than all other building sizes. Now comes to the product type. Here we only divide it into two types, which are investments, properties, and owner occupied. Certain areas are heavily owner occupied, and some other areas are very attractive to investors. And these are very important because uh, when the housing transaction type are different, people are the expectations that the buyers is likely to pay or the sellers would likely to sell is very different between these two type of purchase transactions. Product type by building year. This is very interesting that the older buildings are generally for investing, while newer constructions are predominantly owner occupied. there might be some problem with these features, which I will be mentioning later in this presentations, that I will exclude these features from the model training because this does not logistically making a lot of sense. I believe there is some problem with this with this features. Um, Now let's go to the feature selections. So the main methodologies that I used for feature selections is using XGBoost sorts out the housing features by its F scores. That is to say, now I have like 200-ish features. I pull all of these 200-ish features into XGBoost, let it run, and going back and forth, and then I got its performance. And it shows you there is a function in XGBoost package allows you to see the F score, which tells you the feature importance of each features. The F score is higher means the features are more important. So what I did is I doing a set of iterations. Every time I remove the least important features from the feature sets and retrain the model to see how is its performance, to see if it is the performance is improving or not. Um, and I every time when there's a improvement, I remove more least important features and to see if the model's performance improved. Once the model performance does not improve anymore, I stop and I know these features are the most important features. And so that the previous was used to select the real estate related features, and I used the same methodologies to choose the macroeconomic features, and then I came up with the top 45 ranking features. And based on these 45 features, I also do other feature engineering. For example, so in the real estate related data, there is a lot of distant related features like distance to the nearest schools, to the hospitals, to the nearby attractions, and I integrated them by averaging out the chosen distance related features into an average distance features. That allows us to have a more comprehensive about the actual location of this property. So this is just one. Like I previously mentioned, I also doing feature engineering on the unit price. This is another feature engineering that I did when training this model. Now let's go into the data cleaning. Um, there are mainly two parts. One is handling the outliers. Um, I mainly use the main value of certain of the selected features like square related features and distant related features, and imputed by the mean within subareas if the value is considered as an outliers. And for the missing values, there are three main type of features. First thing is the building years. If it is missing, which is obviously building years is very important features when real estate transactions. It will imputed by most common build years in sub areas because usually the properties in a neighborhood usually will be developed in a certain time frame. So their build year should be similar to each other. Number of rooms will be imputed by the average number of rooms by a similarly sized apartment within the sub area, and also the states was also imputed using the build year in the sub area. Model selections. So in this project, I mainly choose three types of models. to train the data and see their final performance and select the best performed model as my final results. So here I choose multiple linear regressions. There's certain pros and cons. First thing first, is very easy to interpret, simple to implement. However, it has a very obvious con that it cannot handle multicollinearity well, especially when you see this high number of features and they're highly related to each other. Second is the gradient boosting trees. It has high predictive accuracy, but sometimes it's slow to train. It has high number of parameters, and also it requires all missing values to be imputed. But sometimes if you cannot handle the missing value pretty well, it will brings you noise and biases. And the last not but the least, I choose XGBoost, which is a very popular model that used in the Kaggle competitions. It brings you a very high perform predictive accuracy, accepts missing values, but also has some columns relatively faster train compared to GBM, but higher number of hyperparameters. So let's look at these model trainings process one by one, multilinear regressions. So you have to check uh, uh, prerequisitions uh, of certain principles before using multilinear regressions like this. And when I tried to use this, I found a series of violations of its principles. First thing first, violations of multicollinearity. As you can see here, the green cell means there's a positive correlation between two features, and the red means there's a negative correlations. And you can see there's a lot of green cells and red cells. So there's a violation of multicollinearity. Violation of linearity. Here is a scatter plot matrix among those important features. You will see some of them are highly linear with each other. A violation of constant bias. This is a residual visit versus fitted values, again skewed. Violations of normality. So all in all, it is not a great choice to use multilinear regression to train this type of complicated situation, complicated data sets. To improve this type of situation, I would use principal PCA to remove those multicollinearity. There will be a slightly improvement in the performance. However, it still cannot remove all those problems while you're using this. So when you're dealing this type of complicated questions, I would always recommend to use those uh, tree-based model, gradient boosting models that allows you to handling more complicated uh, data sets. Gradient boosting models. So for each gradient boosting models, we use cross validations to tune the parameters. And here you can see the average. What are the parameters that I use, and what are the prediction results, and followed by XGBoost. The training process is very much similar to each other's. You have to tune those hyperparameters. The quick speed in the training a model is a result of allowing residuals to roll over into another tree. Carefully select those hyperparameters such as learning rate and max deeps will save you a lot of time when um, doing the hypertuning. And these are the final parameters that I use in the final results. So let's look at the prediction scores. How Kaggle competitions gives you a result. So it gives you training data sets, give you test data sets. When you use your training data sets to train the model, the model is ready, and then you use those test data to predict a list of single column of prices of those houses, and you upload the results to um, to the Kaggle websites, and each user will have only 4 chances of submitting their results within a day. So here is what I got. The public score of Kaggle, which is RMSE, we use as the final metrics to evaluate whether the models performs good or not. RMSE is is basically the lower the better. So here we can see the multilinear regression. We choose um, simple features, but eventually gives the worst um, results. It is easier to interpret, but does not give you good results. Gradient boosting, um, final result is 0.347, and the best results is given by the XGBoost, which we used at the end. We use 292 property specific features plus additional engineering features, and it gives me the best results, which brings me to the top 10% of the final 3,500-ish teams. Um, Although it is less interpretable, the black box XGBoost model performed the best, surprisingly. Um, and Now that we have seen how the models works in the practice and learned how to best communicate with our results with one another, um, we can now better plan to how to use the machine learning models to solve a real world questions in our later real world projects. That's it. Thank you very much.